So in this video, we are going to be assigning configuration by looking at the structure of a molecule. And then at the end, we're going to talk a little bit about how you would go about resolving enantiomers. So remember, enantiomers are non-superimposable mirror images. They're stereoisomers, and they have identical physical and chemical properties. Well, chemical as in reactions in the lab, but biologically speaking, not so much. So it's kind of like a lock and key kind of a thing. So like we said in the last video, you can't put your car key in the door to your house and expect it to work, that kind of a thing. So we're all pretty familiar with that. Same thing goes with these molecules. So they have a handedness about them. In other words, in three-dimensional space, they're going to occupy that volume a little bit differently. And our receptors, so in our plants, animals, whatever, the receptors that we have for these molecules also have a handedness, or they can have a handedness. And so in this video, we're going to assign configuration by structure, and I want to introduce something new. So instead of just looking at a tetrahedron, let's look at an actual full-on molecule. So we'll start off with a tetrahedron just so I can show you something called a Fischer projection. Fischer projections make things just a little bit easier. It makes it easier to see what's coming out at you and what's going back into the page, especially for molecules that have more than one asymmetric carbon or more than one stereocenter. So we are going to introduce the concept of Fischer projections. These work really great for amino acids, for sugars, etc. Molecules that have more than one asymmetric carbon. The good old tetrahedron is great for one single stereocenter. But what happens if there's two or three or four? What if you have a molecule, like estrogen or testosterone or glucose or something, where there's definitely more than one asymmetric carbon? I want to talk about how you can predict the maximum number of stereoisomers and how many enantiomeric pairs you can expect to have. So with the Fischer projections, I'm just going to start out with an example. So these will make it easier. To visualize what's coming out at you or pointing at you, and what groups are going into the page. Or the back of the molecule. What's front and what's back? In other words, so the best way to start these is to just give an example. So I'm going to use the last molecule that I think we may have talked about in the last video. And this will have just one asymmetric carbon, but we want to make different groups. So here's our chiral carbon. That particular carbon has four totally different groups on it. There's a methyl group, there's a hydrogen, there's a bromine, and there's an ethyl group, right? In the first step, what you're going to do is you're going to find the chiral carbon. We just did that. In the second step, what you want to do is you want to draw a giant cross. So we're going to do like a line bond structure for this. So we're going to do this. And in the middle of the molecule, you have your asymmetric carbon. So that's how we're going to view this. The other thing is that when we assign where these groups go, we're always going to put the lowest numbered carbon at the top of the cross. So because we have some sort of a butane going on there, and we have a bromo group on one of the inner carbons, remember it's the only substituent you have, and with nomenclature for alkanes that have substituents, just one substituent on it, we're going to give priority to that substituent because it's the only one there by giving it the lower number, right? What that means is that bromo group's hanging off the second carbon. And so what that really means is the methyl group to the left is the lower numbered carbon, right? So we're going to put that at the top of the cross. And at the bottom is going to be the other end of the molecule. So the ethyl group goes down here. Now you can put the hydrogen and the bromine on either side. It's no big deal. Pick whichever you want to start. We'll just do that. And initially, when you draw it like this, the meaning of these, this is a Fischer projection. So the meaning of this is such that the lines that are vertical are indicating that the groups are pointing back away from you. The horizontal lines are indicating that the groups are coming forward, almost like they're giving you a hug, right? So vertical lines, so I should say initially, your vertical bonds on the cross indicate that those groups are going back, and horizontal lines, in other words, the bonds that are hooking up to the bromine and the hydrogen there, those are coming forward, like they're about to give you a big hug, right? But here's the deal. You have to assign priority to these groups, just like we did before. So whatever is the heaviest, right? Starting with your chiral center, you're going to move out in any direction. You're going to assign top priority to the heaviest atom. So the heaviest atom is going to be the bromine, right? And the least heaviest or the lightest is going to be the hydrogen. So in a Fischer projection, what you're looking for is the lowest priority. So the hydrogen is really what you're looking for here, and you want to make sure that the hydrogen is pointing back. When you put your Fischer projection together, if your hydrogen is not pointing back, and usually it isn't, right, because we're drawing the whole molecule from top to bottom, as in lowest numbered carbon forward. So the hydrogen, if it's one of the groups on that asymmetric carbon, will always be on the horizontal, right, or almost always anyways. You're going to have to assign configuration and then reverse it. Or you can say, find the lowest numbered group and make sure it's pointing in the back. But you look at the structure that you just drew and you say, hey, right in this particular structure, this Fischer projection, the hydrogen is pointing at us. It's coming forward, right? Because it's on a horizontal line. What you'll do is you'll rotate this thing 180 degrees, like before, and you can draw, just like we just indicated, the vertical lines going back and the horizontal lines coming forward. But when you rotate this thing 180 degrees, then these groups, actually, let me do this for you. I was drawing the original structure. If I rotate this 180 degrees, then what I end up with is these groups coming at me. That is one hell of a bond. And these groups will be going back. So to make it just make a little bit more sense, let me say, or it looks like this initially, CH3. So I'm going to take that group I was about to draw it like this for you. So this is what you're initially looking at. And initially, the hydrogen and the bromine are pointing at us, right? But we're going to flip this 180 degrees. And so now all of a sudden, we have this, right? So all we did was flip that 180 degrees. So what we have now is a situation where we can assign priority. So we're going to take our heaviest atom. We're going to say that's our top priority. Our next heaviest atom Well, in either case, top or bottom, we hit a carbon. But if you keep going, in the top situation, that methyl group, the next bond would be to a hydrogen. And in the ethyl group, the next bond would be to a carbon. So this is going to be number 2. This will be 3. We already knew this was 4. So what you have here is a clockwise rotation, and we're going to call that R, right-handed. What you could do, now you don't have to draw it like this and flip it and redraw it, and that's annoying, right? What you could do is say, assign configuration to your original molecule. So we could do it the same way. I'll just color these differently just to show you that we're taking another stab at this. But this is going to be this time without redrawing the structure, because that can be annoying. We know the hydrogen is our lowest priority. We know that the bromine is our top priority and ethyl comes next. So in this situation, we have a counterclockwise rotation, which would normally be S. What you can say is, all right, this is the way I initially drew the molecule. Hydrogen is on the horizontal, which means it's coming out at us. It should be going behind us. So let me assign configuration to this molecule as it is. And if the hydrogen is not pointing in the back, we'll reverse the configuration. So you would initially say that this was an S configuration. This was a left-handed molecule, but the hydrogen's coming out at you. So then you say, nope, this is right-handed because hydrogen's on the horizontal. Or you could go ahead and just redraw the whole structure. Not too many people are interested in doing that, especially when we start drawing bigger molecules like sugars and such. So it's easier to say hydrogen's on the horizontal. That means it's coming out at me. So whatever configuration I assign, I'm going to reverse it. Most people enjoy doing it that way instead. So these Fischer projections are really nice for bigger molecules. So let me give you a couple of examples. You can do this just by looking at the structure. So instead of drawing out the cross, you could say, what if I'm just presented with an actual molecular structure? So in this particular case, I have a situation where I only have one asymmetric carbon, but what if I have a bigger molecule with more than one? Or what if I have something like an amino acid or some kind of, sugar or whatever, and it's easy to spot. There's only one asymmetric carbon, not such a big deal, right? Let's do a couple of other examples. So let's take an amino acid. So without drawing the Fischer projection, I want to show you how to do this just by looking at the structure, because often you'll see these written like this, right? So here's an amino acid, and say you're presented with stereochemistry. See how there's a dashed line on the molecular structure? That tells you that this is an asymmetric carbon. They're telling you there's a stereocenter there. Otherwise, they wouldn't be indicating a dash or a wedge, right? So in other words, because this is a line bond structure, we're not indicating there's a hydrogen there, but because there's a little dashed line going to the amino group, the hydrogen, which is implied, is coming out at us. So you can make your life a little bit easier and draw it in if you like, or you don't have to. Just say the hydrogen is implied, it's the fourth group, and it's coming out at us. So then what you can do is say, I'm going to assign configuration. I'm going to circle my top priority group. So if I go from that asymmetric carbon out, I notice that I have a hydrogen. That's an easy number 4, right? That's the lowest atomic mass. If I go up, I hit a nitrogen. If I go to the left, I hit a carbon. And if I go to the right, I hit a carbon, which makes this group heavier. Nitrogen is a little bit heavier than carbon. And then you have to decide, if I go to the left, I hit a methylene, so that's a CH2, right? If I go to the right, I hit a carbon, an sp2 hybridized carbon that's part of the carboxylic acid. So I hit a carbon in either direction, so you have to keep moving. And you say, all right, if I keep going, on the left, I hit either a hydrogen, or I can go further and hit a carbon. On the right, I go down, I hit an oxygen, or I go further to the right and hit another oxygen. That helps us decide that this group takes priority. Oxygen is heavier than carbon or hydrogen. So that's going to be number 2. And then this over here, this benzyl group, has to be number 3. So if I want, I can assign configuration right here, and I can say 1 going to 2 is clockwise, right? And if that's clockwise, it's R. But then you have to say to yourself, the way this was written, somebody indicated that the amino group was pointing in the back. The hydrogen should be pointing in the back, right? So I've assigned an R configuration, but this molecule is S because hydrogen, as it's drawn, is coming out at us. So again, you assign configuration, you look to make sure the hydrogen's in the back. If it is, you keep the configuration you assigned. If it isn't, you put it in the back and you essentially flip the molecule. So this ends up being S, but it's an amino acid. And for amino acids, we use L typically. It's not wrong to use an S, but if you go out to buy a little pile of supplements and you're looking for amino acids, or if you're looking for a sugar, D and L are usually what we use to indicate handedness. And this is phenylalanine, abbreviation Phe. So let me show you another one. Let's draw one where whatever you assign is actually the, you don't have to flip it. So let's go ahead and draw this. So we'll put this group coming out at us, which means that the hydrogen that's implied is pointing in the back. Here's something somebody asks me almost every semester. How do you know the methyl group is not pointing in the back or the carboxylic acid? Because they've drawn it for you in the plane of the page. So if the other group is implied, it's because the wedge is going to the hydroxyl group, then you assume that the hydrogen that's implied is going behind. The rest of the molecule is drawn in the plane of the page. So it would be like if you're doing a tetrahedron and you had 2 bonds in the plane, that's kind of what's going on here. So we have our asymmetric carbon. We have a hydroxyl group that's coming out at us. This is going to be our top priority. The next option you have is to go to the right or the left. If I go to the right, I hit a carbon. If I go to the left, I hit a carbon. But if I keep going, on the left-hand side, I only hit hydrogens. On the right-hand side, I hit oxygens. So this will be group number 2. This methyl group will be group number 3. And the hydrogen that's implied is going to be group number 4. You can draw it in if you want. You don't have to. But because the hydroxyl group was drawn for you as coming out, then this has to be going back. So then you're just going to assign configuration. 1 going to 2. This is a counterclockwise direction. This would be S. And then the next question you have to ask yourself is, at that asymmetric carbon, is my lowest priority group pointing in the back or the front? And the way that they've drawn it for you, the hydroxyl group is coming out at you, which means the hydrogen has to be going behind. So the configuration that you have assigned is fine the way it is. So this ends up being S, and this is lactic acid. So this is great. We only have 1 asymmetric carbon. What happens if you have a molecule with more than 1 asymmetric carbon? What if you have, like 2, for example, right? Or if you've got 3 or 4, or if you have 16 or whatever, you got a hormone going on, you have like 5 or 8 asymmetric carbons. This gets like pretty complicated pretty quickly. So for isomers with greater than 1 chiral carbon, or more than 1 stereocenter or asymmetric carbon, whatever, we can say that the maximum number of stereoisomers, and the word max is kind of important. Oops. The word maximum means that it's the most you can get. It doesn't mean it's the amount you will get. And I'm going to give you an example of why you might not get the maximum number. The maximum number of stereoisomers for any molecule with greater than one stereocenter or greater than one chiral carbon is going to be equal to 2 raised to the n power, where n is going to be equal to the number of chiral carbons. So if, for example, you have a molecule that has 2 asymmetric carbons, the maximum number of stereoisomers that you should be able to get would be 4. In that case, you would have 2 pairs of enantiomers. There are situations, so let me write this down here, it's kind of important. There are situations where you can get less than the max. So when can you get less? This will be where you find a plane of symmetry in the molecule. So look for a plane of symmetry. In other words, you will have meso compounds. So let me draw you an example of that. So for example, if I have a molecule like, take something similar to what we just drew and add an extra asymmetric carbon. Not hard to spot where the mirror plane is going to be, right? But go ahead and draw your, let me move this over to give us some space here. Go ahead and draw your Fischer projections. So what we're going to do is we're going to give the lowest numbered carbon to the top position, but this thing looks pretty symmetrical, right? So these are pretty easy to spot. We'll draw Fischer projections. So the first methyl group will be up here. And instead of drawing the cross, now we're going to do the same rules, but we're going to put, there's 2 chiral carbons here, right? And those are going to be in the middle spots. Essentially, we have 2 crosses that are hooked up. You can do this for as big of a molecule as you like, right? With these, with the 2 asymmetric carbons, so I got one here and I got one here. What I like to do, and you don't have to do it this way, but it's easier to keep track if you have multiple stereoisomers. I like to stick all the same groups on one side for the very first molecule and then draw its enantiomer. At least then you knock 2 of them out of the way. What do I mean by that is I'm going to put both hydrogens on the right to start out, and I'm going to put both bromines on the left. And I'm going to draw my little mirror plane here. And I'm just going to bang out its enantiomer. So you have 2 stereoisomers. So if this is looking in the mirror, this is what it sees. So here's the thing though. Notice in this molecule how there is a mirror plane here or here. If this thing looks down at itself, it sees the same thing on the top as it does on the bottom, right? So this is going to be a mirror plane of symmetry. So we have a symmetric situation going on here where only one of these stereoisomers counts toward the maximum number of different stereoisomers. These things, if you see that mirror plane, are meso compounds. But it doesn't mean that you don't have other stereoisomers, right? In this particular molecule, the max stereoisomers is going to be 2 to the 2, right? So there should be 4. You expect 4 stereoisomers. But because we have that mirror plane, one of them doesn't count. They are meso compounds. So where are the other 2 then? This is where I'd like to introduce you to the concept of diastereomers. What I'm going to do is I'm going to flip around. See how they're all carbon-carbon single bonds? So we can rotate around one of those bonds. So we're going to do that, but only one. So I'll do the top one. I'm going to put the bromine here, and I'll put the hydrogen here, and then I'm going to leave the other one as it is. Because this is a valid stereoisomer, right? And then I'm going to draw the mirror. Now, there is no mirror plane here, right? If this thing looks down at itself, that bromine on the left at the top sees a hydrogen, not another bromine. So this is valid, right? And I can draw its enantiomer by saying, imagine this thing looked in the mirror. And if it did, it would see hydrogen here, bromine here. Notice how they're different, right? Bromine here and hydrogen here. These are enantiomers. When you see that you have a mirror plane, or you have a plane of symmetry in your molecule, you have a meso compound that knocks out one possible stereoisomer. So when we say the maximum number of stereoisomers that you can get is equal to 2 to the n, you have to really carefully look at the structure. If you can find a mirror plane, then you have a meso compound, and that knocks out one enantiomeric pair. And so in other words, you have one enantiomeric pair here. So I have 2 enantiomers, and I have meso compounds. Okay, what happens when that doesn't happen? So like, what happens then if I have a molecule that simply just has, 2 asymmetric carbons? So what if I had something like this? I'll draw it without stereochemistry to start with. And we'll draw the methyl group in there just for clarity. Okay, so in this case, I have 2 chiral carbons. I got one right there, right? The hydrogen is implied, but obviously on the left, I just have a phenyl group. So I just have that aromatic ring on the left. Over on the right, I have a whole pile of other stuff. And up the top, I have a hydroxyl group. And then implied on the structure, but not drawn in, is a hydrogen. This carbon is also chiral, isn't it? To the right, I have a methylamino group. Down there, pointing down 6 o'clock, I've got a methyl group, and implied there's a hydrogen. And then off to the left, I have that little pile of stuff, that carbon with the hydroxyl group and the aromatic ring. So I have 2 asymmetric carbons. The first thing that you're going to want to do is you're going to want to number the carbons, because we're going to draw Fischer projections. You want to put the lowest numbered carbon on the top. I'm going to help you out with this one just because we haven't done alcohols, we haven't done aromatics, we haven't done amines. Like, you'd have no idea of knowing which carbon was going to be the lowest one just yet anyways. So I'm going to go ahead and just tell you that carbon number 1 is here, and then this is going to be carbon number 2, just for the sake of drawing our Fischer projections. Remember, when you draw your Fischer projection, the first thing you're going to do is put the lowest numbered carbon on the top. The lowest numbered carbon is going to be number 1, and the group that's attached to number 1 up the top would be that phenyl group. So this thing right here, this is known as a phenyl group. I'm going to abbreviate that PH, right? So this is our phenyl group. This is all just, I'm letting you know because we haven't done aromatics yet. And our abbreviation for it is pH. Or you can feel free to draw that little benzene ring, that little oyster cracker looking thing every single time, but I don't feel like doing that. So I'm going to let you know that pH means that group right there. So my first molecule that I'm going to draw is where I put my phenyl group up the top. And it's going to be attached to carbon number 1. That's attached to carbon number 2. And that's attached to the methyl group. Because just like any other molecule, when we number this thing and name it, we're looking for the longest continuous chain of carbons, right? So that methyl group goes down the bottom. What goes up the top? Well, carbon number 1 has what on it? A hydroxyl group, so OH and hydrogen. Now, like I said, I like to put the hydrogens all on one side at first because who cares, right? It doesn't really matter. At the end of the day, you got to draw all the structures anyways. So I think it's easier for me anyways to keep track of the ones I've already drawn if I put all the same groups on one side, if possible. So here we have our methylamino group on carbon number 2, right? And then what we get to do is draw our little mirror because there is no plane of symmetry. So we don't have to worry about meso compounds. And if we do this, what do we see? Well, this thing would be looking at itself in the mirror. And it would see this. And that knocks out one enantiomeric pair. Or in other words, a pair of enantiomers. The maximum number of enantiomeric pairs is going to be equal to your 2 to the n, so the maximum number of stereoisomers that you have divided by 2, right? So up here, if that wasn't a meso compound, I would have had 2 pairs of enantiomers, right? And so the maximum number of enantiomeric pairs would have been the number of stereoisomers divided by 2. In this particular case, we had a meso compound because we had a plane of symmetry. So that knocks out one of those stereoisomers as being unique. So we say we have meso compounds and one enantiomeric pair. This molecule is not like that. This molecule has 2 asymmetric carbons, in other words, 2 stereocenters. And I'm going to go ahead and I'm just going to letter these so that we can keep track of who's who, because I'm going to refer to them by their letters instead of redrawing them. We have structures A and B. Now, what I can do is I can flip around one of those carbon-carbon single bonds. I like to start on the top. You can start wherever you like. But after drawing a number of these over the years, I find that for me, keeping track of things is tough. So I flip one thing at a time, and you create your own system. I start at the top. So for carbon number 1, I'm going to say, why don't I just go ahead and I'm looking at structure A, and I'm going to flip that around. If I flip that around from structure A, right, I get the hydroxyl group over here, hydrogens over here, and I'm not touching carbon number 2. So from structure A, I get this. So I'm going to go ahead and draw like a little divider here. Oof, there's a lot of caffeine. Okay. And I'm going to label this structure C. Notice how if you put that structure in the mirror, you don't get either A or B, do you? What you do get is another stereoisomer. You'll get its enantiomer, won't you? But you won't get A or B. What you end up with here is structure D. It is unique all to itself. All 4 of these are valid stereoisomers, but they are not all enantiomers of each other. So when I say A and C are not non-superimposable mirror images, they're not enantiomers. A and C, looking in the mirror, you don't see the same thing, do you? So these are not non-superimposable images. A and D, same thing. I don't have non-superimposable images there, but yet at the same time, they are all stereoisomers. So they're all valid. What we have here is a pair of enantiomers. These are enantiomers. These are non-superimposable mirror images. These are a pair of enantiomers. I had 2 chiral carbons. Maximum number of stereoisomers should be 4. I have 4 stereoisomers. I have 2 pairs of enantiomers. What is the relationship, though, between A and C and A and D, or B and C and B and D? They are diastereomers. Diastereomers are stereoisomers that are not enantiomers. So A and C and B and D are diastereomers. And also A and D and B and C. They're diastereomers. So let me write that out down here because that looks more confusing than it should be. So A and C and A and D, and then B and C, and then B and D. These are diastereomers. Let me tell you a little bit about these. These are going to be stereoisomers that are not enantiomers. And we can take advantage of this because enantiomers, if you remember, have identical physical properties. If you make this in the lab, if you concoct this particular, if you synthesize this molecule and you get all 4 of these stereoisomers, you get 2 pairs of enantiomers, you cannot chemically, or even, I'm sorry, not chemically, you cannot physically separate A from B and C from D, but you can separate A and B as a mixture from C and D, because diastereomers do have different physical properties. So you could do a fractional distillation, you could do a recrystallization, you could even like do some kind of like a filtration or whatever. I mean, do some chemistry, right? And filter off the enantiomeric pairs. But you're not going to be able to get A and B away from each other in, physically in the lab, or C and D away from each other physically in the lab. What you can do is you can get them away from each other chemically. So I can react a pair of enantiomers with some chiral molecule to then make a pair of diastereomers. And then I can go ahead and separate those. That is called resolution. So resolving enantiomers means you take an enantiomeric pair and you react it with some chiral molecule to make a pair of diastereomers. Go ahead and physically separate those. So distill it or whatever you got to do to physically separate them, run a column, right? Column chromatography, whatever. And then you have separated the diastereomers, and then you can go ahead again and hit it with some more chemistry and liberate the enantiomers by themselves. So you're not ever going to be separating enantiomers physically, but you can separate diastereomers physically. So this is important. These have different physical properties. So therefore, they can be physically separated. So if you're curious about these molecules, what we have here, A and B, just I'll write it over here because it's not really part of the lecture, but if you're curious, what is this molecule in the first place? So A and B, see, this is ephedrine, and C and D, pseudoephedrine. It would be a situation where not too many people care about separating all of these because all of these molecules are biologically active. Ephedrine is a little bit more biologically active than pseudoephedrine. If you're curious, if it sounds familiar, pseudoephedrine was the molecule in the sinus medication Sudafed. They took it off the market because it was very easily, so if you're looking at this molecule up here, this pseudoephedrine was very easily converted into methamphetamine. So blow off the hydroxyl group and you have methamphetamine. I mean, blow off the hydroxyl group in the lab, but not just blow on it and it goes away. So how do you assign configuration to these? So why are we drawing these Fischer projections in the first place? Let me erase some of these confusing lines. So we have these already labeled down the bottom, and we're going to go ahead and we're going to assign configuration using our Fischer projections. So remember, you have 2 asymmetric carbons on each molecule. Also remember that you have your hydrogens on the horizontal, right? And all of your stereoisomers, which means that whatever configuration you assign, you need to reverse it, right? Because all of the groups on the horizontals are coming out at you. These are Fischer projections. So whatever you assign, you have to reverse the configuration. All right, so we're going to start at the top with the first chiral carbon. And so I'm going to say this is carbon number 1, and I'm going to say this is carbon number 2. Right? I'll just do that for the first one, and you can remember we're going to do that all the way across. The top one is carbon number 1. So when I assign configuration, I'm going to put the number before the R or the S in the parentheses. I'm going to separate both of those asymmetric carbons with a comma, and the whole thing will go in parentheses right before the name. Okay, so for the first asymmetric carbon, what I'm going to do is I'm going to find my highest priority group. Obviously, that's the hydroxyl group. And then the next highest priority group is going to end up being the carbon that has the methylamino group attached to it. Because if you go up into the phenyl, it's just carbons and hydrogens. If I go down to carbon 2 and then out, I hit a nitrogen, right? So what I get to do then is draw the way this thing would rotate plane polarized light in this direction. Normally, that would be S, wouldn't it? But the hydrogen is on the horizontal. So we have to be mindful. Let me write that down there. Whatever you assign, will get reversed because the hydrogen is on a horizontal bond. And horizontal bonds in Fischer projections are pointing at you, coming out of the page. Everything on the vertical lines is going away from you. So this is just by convention. We all accept this and say, I have just assigned that carbon number 1 appears to be rotating plane polarized light to the left, but the hydrogen, as I've written it, is on the horizontal. So instead of being left-handed at carbon number 1, it's right-handed. And carbon number 2, if I go out to my top priority group, it's the methylamino group, right? If I go straight up, I hit a carbon and then a hydroxyl group. If I go straight down, I hit a carbon and a pile of hydrogens, right? So if I go straight up, that's my next top priority, which means that I'm rotating in this direction, which would normally be R, wouldn't it? But because the hydrogen is on the horizontal, it's going to be S. So let me do this in a different color so you can see. In parentheses, before the name, before this thing gets its nomenclature, we would assign the configuration and we would say, at carbon number 1, it appears to be rotating plane polarized light counterclockwise, because we've assigned our groups priority based on their mass, but the hydrogen's on the horizontal, so I'm going to reverse the configuration. Instead of S, it's going to be R. And I have to tell you which carbon that is assigned to. So 1R, comma, 2. Now, this would normally be R, right? For carbon number 2, we're noticing that it's rotating clockwise, but the hydrogen is on the horizontal, meaning it's coming out at you. If I flip this thing totally over, right, I would get the opposite configuration. So instead of R, this thing becomes S. And then you would put a dash, like a hyphen, and give the rest of the name. So you could call this 1R, 2S dash ephedrine, right? Or you could give its IUPAC name, which we haven't covered these functional groups yet, so I wouldn't expect you to know that. And the nice thing about the enantiomer is that you don't have to do your little arrows all over again. It's literally the opposite configuration. So in other words, this would be 1S, and this would be 2R. So you just do 1, and then its enantiomer is the opposite. We do have to do C, however, though. So, and then we can just reverse that for D. So again, we're going to go in the direction of rotating the plane polarized light in the direction according to the priorities that we set. So the hydrogen is our lowest priority. The hydroxyl group is top priority. So this is going to go like this, right? So that's normally R. That's clockwise rotation. But again, hydrogen's on the horizontal, so we're going to reverse it. In carbon number 2, right, we're going to say that this is going in this direction. Normally that would be R, but because again the hydrogen is on a horizontal line, we reverse the configuration. So for this stereoisomer, for carbon number 1, that originally was going clockwise, so that would have been R. That ends up being S. Carbon number 2, that was also going clockwise. Again, hydrogen on the horizontal makes it R. Or I'm sorry, it was R, it's going to be S. So it was clockwise. And we're going to say it's left-handed. If you want, you can just picture picking up the phenyl group and spinning this thing 180 degrees. Most people just say it's easier to assign configuration, find out where the lowest priority group is, and just give it the opposite instead of redrawing the whole molecule. The diastereomer of A and B would be C and D, right? The enantiomer of C would be D. So what that means is all I have to do is reverse the configuration. So that would be 1S, 2S pseudoephedrine, or 1R, 2R pseudoephedrine. So that's how you would assign configuration using a Fischer projection. Up here, we talked about assigning configuration based on structure. Where did it go? So by structure, what I mean is somebody has indicated the stereochemistry by using dashes and wedges. If someone doesn't indicate stereochemistry by using dashes and wedges, you find the chiral center and draw a Fischer projection. So why is this so important to us? We've been talking all along about biological relevance, right? So you can take a molecule. I think in the other video I just referenced LSD. It was the thing that just popped into my head because I know it has an asymmetric carbon, and one of the enantiomers is completely biologically unreactive. Like doesn't do anything to you. But the one that is reactive, I'm pretty sure everyone can imagine what it does to you. So there's a huge difference sometimes for some molecules. This particular little crew of molecules, not so much. 4 stereoisomers, they're all biologically active. 2 of them, one of the enantiomeric pairs, A and B, is a little more reactive than the other, right? Sometimes you can have one that's reactive and one that's not reactive, and other times you can have one that's reactive and one that will kill you. So it's kind of important that you know what's going on. Just generally speaking, though, in terms of biological relevance, stereoisomers can be active for good or bad. Meaning, like, you take a medication and it's doing what it's supposed to do for you, I would consider that good, right? Or bad, you take something and it's not so great, like you're done, right? One and done on that one. Or not active. In other words, your body doesn't react to it because the receptor is not matching the handedness of the molecule. And in that case, nothing happens. Or it can be mildly or say a little less reactive, like pseudoephedrine compared to ephedrine, right? So in terms of biological relevance, something that might stand out to us would be amino acids for humans are left-handed. So this would be for us, right? Some other creature, like bacteria, for example, may use the D. Sugars, so carbohydrates, for us, D. So if you go into a vitamin shop and you want to buy an amino acid supplement and you're looking, say, specifically for like arginine or whatever, lysine or something, note the difference in price. When they give you, when they, in little letters down the bottom, and you think you're you think you're reading the shelf wrong, and you're like, this is $8.99, and the other one is like $17.99. I'm gonna just grab the $8.99 one. What you're getting, if you see in little letters on the label, is a mixture of D and L isomers. Your body won't recognize, if it's an amino acid, your body won't recognize D. Nothing bad happens. You'll just excrete, um, but you're really only getting a certain percentage. And if you turn the bottle around, they should tell you, because they can tell you the percent, the ratio of one to the other. If it's a 50-50 mix, then you might as well buy the more expensive one, right? If it's just double the price. How do you separate these things? Why would one isomer be more expensive than the other? Because they had to resolve the enantiomers. That's not free. Somebody had to do it, and it took reagents. So let's talk just a little bit about separating or resolving enantiomers. Because remember, these things have identical physical properties. So you're not going to be able to just simply distill um, a racemic mixture and expect that one enantiomer is going to come out before the other. One of them is not going to have a different boiling point. Not even a fractional distillation is going to make a difference. They have identical boiling points. So they'll just come out together cleaner than they were before you distilled them, but they're still together, right? So what we can do is we can allow a racemic mixture to react. So that'll be a 50-50 mixture of enantiomers is a racemic mixture. And we can allow that mixture to react with a chiral molecule. And we'll just keep it generic and say that we're going to chemically convert a pair of enantiomers to a couple, I should say, to two pairs of diastereomers which have different physical properties, and you can separate those. Then we're going to separate the diastereomers because they will have different physical properties. You could potentially do a fractional distillation and separate the diastereomers. And then after you do that, you hit this again with work, like acid base workup or whatever, to resolve the enantiomers. What do I mean by that? Well, let me just give like a small example. We'd say, take a carboxylic acid. I'll draw it like this so we can see the asymmetric carbon a little easier. Put our hydrogen in the back. So what can we have? We'll just keep this simple and do a methyl group and a hydroxyl group. Okay, so here I have the R isomer. I'm going to go ahead and draw the S. We'll just, for the first one, show you. So this is a pair of enantiomers, right? We're going to take this pair of enantiomers and we want to separate these. But because they have the same boiling point, they have the same melting point, they have the same, physical properties, I'm not running these down a column. I'm not doing a distillation. None of this, right? I'm not doing a recrystallization. I'm never going to get these guys apart, but I can react to them because this is a carboxylic acid. This would be just an easy kind of example. I'm going to react this with a chiral base. So we'll just pick a left-handed base. Doesn't even matter what it is. We'll just say S base, some molecule that is left-handed. And then what do I get? I'm going to get a pair of diastereomers. So what I do is I'm going to deprotonate my carboxylic acid. So that's going to end up being negative. And then this will be my, we'll say S base conjugate acid. So I'm making a salt here. Just draw on that first molecule, deprotonated. So all I did was salt this thing out, right? And then over here, I've got the same thing, CO2 negative. So I have my salt. These are diastereomers. So long story short, I have taken a pair of enantiomers, right? And I have allowed the mixture, the racemic mixture, that is a 50-50 mixture of enantiomers to react with a chiral molecule. In this case, it's just a left-handed base that I decided to choose, right? So these diastereomers have different physical properties. And so I can separate them. Over here, can't separate. And what I'm going to get is CO2 minus, and my S, my left-handed base, conjugate acid. I have hydrogen here. I have my methyl group coming out at us. Hydroxyl group. These are separated now. Just redrawing them. S dash base, H plus. So what I have here, right, is a salt. What I can hit this with, now that these are separated from each other, with some aqueous HCl, reprotonate the carboxylic acid, and instead of redrawing this, since this is just a video, I'm going to cheat. I'm going to take that down there. And I'm going to take this, and I'm going to do the same thing. Sometimes in the lab, I wish we could do this. Let me just circle the molecule instead of purifying it. And duplicate it and put it down here and then erase things. So this is what you get. And carboxylic acid back again. And what do I have? I have my RS salt. So essentially you might be sitting there going like, what are you talking about, a diastereomer, right? Here I had an R molecule, but now I have the S salt attached, right? The other one, I had the S isomer, and I have an S salt, right? RS and SS are diastereomers. RS and SR would be enantiomers. So here we have created diastereomers. We're going to separate them. What do I have down here? I have RS salt down here. Over here, I have my SS salt. Because remember, my base was S. And when I separate these, what do I have? I have the R acid separated from the S acid. Now these are separated from each other. So before, these were a mixture. And now we have separated them. You separate the diastereomers and then work them up, and you've resolved your enantiomers. So this right here is the reason when you go to buy an amino acid supplement or some supplement that has handedness about it, and it costs more for one enantiomer, someone had to do something to get these things apart from each other. Okay, so that's going to do it for chirality and stereochemistry.